All right, today we're going to start talking about energy. What was our topic last class? Work. Okay, and what's the equation that we found for work? Force times distance. Okay, force times distance is work. And what's the unit for work? Joules. Okay, today we're going to kind of segue into energy. Okay, energy is the most important topic and the baseline of most sciences. Okay, energy is conserved. Okay, and so we're going to talk about that today. We're going to talk about two big types of energy. Do you know what those two types of energy might be? Kinetic and potential. Good, good. Okay, we're going to look at translational energy. Okay, translational, kinetic, and potential energy. Does anyone have any idea about what we mean when we say translational? It's moving. Good. When you translate something like in geometry, you move it from point A to point B. So this is what's happening in our motions of this chapter. We're only looking at translational as opposed to rotational. Okay, so we're not looking at anything that's rotating at this point. We're looking at things that move from point A to point B in a pretty simple path. Okay, does that make sense? Translational. All right, when we look at energy in this chapter, we're looking at energy as the ability to do work. Okay, and we're talking about our physics work here. So we're going to have a connection between energy and work with a couple different equations. Okay, we're going to be able to join those two or see the relationship between energy and work. Okay. So we're going to look first at kinetic energy. It's the energy of motion. Okay, kinematics, we studied those kinematic equations for things in motion having to do with velocity, acceleration, all that kinds of stuff. We're going to look at kinetic energy as the energy when an object is in motion. Okay. Kinetic energy can be transferred from one object to another. Do we have any idea as to how that could happen? How can I transfer kinetic energy from one thing to another? Yeah, like a collision, okay, exerting a force on something. Okay, so if one object exerts a force on another object, the second will then have a distance that it's traveled. Okay, if the force is great enough, which means work has been done. So energy has been transferred there. Okay, if I swing a bat and hit a ball, I've then transferred kinetic energy from my bat to that ball. I've also exerted a force which makes it travel a distance, which means work has been done. So there is a connection between the two. Okay, so our kinetic energy equation is this. Ke, which is a really clever, abbreviation for kinetic energy, I know, 1/2 mv squared. Okay, your book shows it as capital K, capital E. I was taught, and I most of the time write it as K subscript capital E. You can do either way. Okay? But those both mean kinetic energy. Okay? 1/2 mv squared. This is translational, not rotational. Okay, you won't have any problems right now that you'll have to do a differentiation between the two. We're only going to be looking at translational in this chapter, but I want to make sure that we understand it's just this simple point A to point B type motion. It's not rotating. We're not having to look at the spin. We're not looking at any of that kind of stuff. Just simple velocity, distance. Yeah, good. So kinetic energy, the change in kinetic energy will equal the net amount of work that is done. So this is another verification that our kinetic energy unit should be joules if it's equal to the work that's done. Okay, so the way that you label this right here could be final and initial. It could be KE and KE sub 0, however you want to label it. This is how your book chose to, so I was trying to be consistent, but this is the second point you're looking at. This is the first point you're looking at. Okay? So net work done is equal to the change in kinetic energy. This very cleverly was named the work energy principle. Okay? It's a connection between work and energy. Okay, these guys are really, really creative. The work energy principle is going to be essential for both kinetic and potential energy when we get to that part. But for now, you need to know that this equation right here is what we consider the work energy principle. That net work equals the change in kinetic energy. Have to remember here we were looking at the work energy principle is that we're dealing with net work, which means it has to be our overall every single thing. Okay, it cannot be frictional work or gravitational work or applied work. It's got to be the net. Okay, so it's got to be the total, not just one of those forces. Okay, it has to be net work. You might want to make a little underline or a star by this work energy principle. Okay, so if I ask you what the work energy principle is, you need to know that that's net work equals change in kinetic energy. Okay? Okay, so this is going to walk us through 3 different scenarios here about work and its connection to potential energy. If you want to write these down, great. It is important that you understand the connection between the 3. There's definitely a way that you can shorthand this in your notes so you don't have to write every single word, but I want you to see the connection, okay? So work energy principle tells us that if positive net work on the object is done, then kinetic energy increases by some amount that is equal to W net, okay, or the net work, okay? If negative work is done, then kinetic energy decreases, and if no work is done at all, the kinetic energy remains the same. Okay, so I want you to think about it as this. If an object has come to a stop, okay, it's moving with some speed and it comes to a stop, what is its kinetic energy at the stop? What's its kinetic energy when it comes to rest? 0. Okay, so if I have work equals kinetic energy 2 minus kinetic energy 1, and if I have this, we know that kinetic energy equals 1/2 mv squared, 1/2 mv squared. Okay, I'm just kind of walking you through these examples here, but if I have a point where it comes to a stop, my speed must then be what? At this point, my second point, if it comes to a stop, my speed would be 0, which would make my kinetic energy 0. Okay, so if I take a 0 minus some number for kinetic energy, my net work must be 0. Or it must be negative, I'm sorry, must be negative. Okay, so that's this second scenario here. If negative work is done, then the kinetic energy decreases. So when something slows down, its kinetic energy decreases, which means negative work is done. When something speeds up, it increases, which means positive work must be done. If the speed does not change, then no work is done. Okay, or if the kinetic energy is not changed. So as something rolls down a hill or as something is dropped, it's picking up speed, it's picking up kinetic energy, which means positive work is being done. Okay? That makes sense? Conceptually, is it fitting together? Okay, kinetic energy is measured in joules, just like work, and it's a scalar quantity. What's that mean to be scalar? No direction. Good. So this says 145 gram baseball is thrown with a speed of 25 meters per second. What is its kinetic energy and how much work was done on the ball to make it reach this speed if it started from rest? So before we do anything, we need to convert our mass into kilograms. Okay, so if we go from grams to kilograms, we move the decimal 3 places to the left. I'll let you finish writing this down and then we'll get going, plugging things in. So we have our mass, we have our velocity, which is what? 25. Okay. Is this going to be our first velocity or our second velocity? Yeah. Second, because it says it starts from rest. Okay, so that means v sub 1 should equal 0. All right, so if I want to find kinetic energy, I'm going to take 1/2 m, so 0.145 times v squared. And I get what number? Okay, good. Thank you. 45 joules. So now if I want to find work done, I take work equals kinetic energy 2, or KE2 minus KE1. What's my kinetic energy 1? 0, because it starts at rest. So that means I'm going to get rid of this. No, we know that it's 0. We know our KE2, since we just solved for it, is 45. So our net work will also be 45 joules. Will our work be positive or negative? Positive, because there's an increase in speed. Okay, there was an increase in kinetic energy. Since our kinetic energy was positive, that means that our work should also be positive. Okay. Questions with this? Okay. How much work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? Okay, so if we want to find net work, we're going to take 1/2 m times v2 squared minus 1/2 m v1 squared. Okay, are we clear where these equations came from? Right, those are both kinetic energy equations. This is for my final, this is for my initial. Okay, so our net work, we'll take 1/2 1,000 20 squared. Oops, sorry, 30 squared minus 1/2 1,000 times 20 squared. Good. Okay, does it make sense that our work here is positive? Yeah. Okay, because we have it's accelerating. We have an increase in speed, so it should be accelerating. If I had asked what the work done to go from 30 to 20 would be, how would our work change? It would be negative. Okay, our work would be negative if we were decelerating. Okay, that's because the forces that would be making it decelerate, like friction or like a brake being applied, are negative forces. Okay, which means that our work should be negative. Okay? Conceptually, is it making sense? Okay. Let's look at potential energy now. Yeah.
So on this equation, you just do.
Okay, so when we're talking about potential energy, we need to talk about where this object is. Okay, is it at the top of its path, at the bottom of its path? It has different potential based on where it is located. Okay? If I'm holding something heavy, or if I'm holding an object up high, do you think it has more potential energy or less potential energy than when it's falling? It has more when I'm suspending it up high. Okay, as it starts to move, it starts to transfer to kinetic energy and it loses potential energy. Okay, so this type that we're talking about here is gravitational potential energy. Okay, potential energy that is kind of taken or controlled just by gravity. Okay, so when a heavy brick is held in the air, it has potential energy because of its relative position to the earth, which is controlled or, I guess, I can't find the word that I want to say. Its position relative to the earth, which exerts gravity. That's what I'm looking for. Exerts. Okay. Besides just the potential to fall and the potential to gain speed and gain kinetic energy, it has the potential to do work on another object that it lands on. Okay, so if I'm holding something heavy and there's a stake in the ground, if that object lands on that stake, it will exert a force. It may move it a distance, which means that work has been done. Okay, so that potential energy can also transfer to work. This is gravitational potential energy. The subscript G is there just for kind of convenience. It doesn't necessarily need to be there, but I put it there for convenience. Okay, so potential energy equals mass times gravity times y. What do you think y would be here? The height, yeah, good. The distance vertically that something falls or is lifted. The higher off the ground it is, the more potential energy it has. If this is y, that should make sense. If this is our height, the bigger that number is, the bigger this number will become. Okay, so higher off the ground, the object is greater potential energy. So here's our work done by gravity equation right underneath there. Okay, work done by gravity is equal to negative delta PE. So negative delta potential energy. Why do you think it's negative? Yeah, it's going down. Always work by gravity will be going down. So we just do negative delta PE. You can combine these equations into the one shown below. So if I had work equals mgy minus mgy. Okay, these two terms are the same. We can combine those terms and just have a y2 and a y1, which is what this equation here shows us. Okay. Again, not a huge deal if you do it this way. It's going to come out exactly the same. This is just a tiny, tiny shortcut. So this is our connection between work and potential energy. This says a roller coaster that weighs 1,000 kilograms moves from point A, then up to point B, then to downward to point C. So here's what our roller coaster kind of looks like. A, B, and C. Okay, from point A to point B is 10 meters. From point B to point C is 25 meters. Okay, so we want to calculate gravitational potential energy at point B, okay, and then again at point C. So we'll start with point B here. Okay, potential energy is equal to what? What's our equation for potential energy? mgy. Okay. So we need to take our mass, which is 1,000, times gravity, which is 9.8, times our height, which is We're just going right now from point A to point B, so we're going up 10 meters. Okay? Okay, that's what I got. 98,000? Okay. So tell me why it would be an increase in potential energy as it goes up the track. Yeah, because it's going higher, which means we have more potential energy. So it makes sense that it should be a positive there, okay? So now let's find the gravitational potential energy at point C. So from point A to point C, our mass stays the same, our gravity stays the same. What's our y from point A to point C? Exactly, negative 15, because it's going below where we started, 15 meters. Okay. What'd you get, Olivia?
Negative 147,000.
Okay, we agree? And why would our potential energy here be negative? Yeah, it's closer to the ground. Okay, so we're losing potential energy as it goes down the track. Okay, we're losing potential energy, but what are we picking up? We're picking up kinetic energy. Okay, we're going to get to the relationship between the two. We need to understand as we lose one, we gain the other. Okay, as it gains speed, it's picking up kinetic energy, but losing potential. Okay? All right. Okay, what's the change in potential energy when the coaster goes from point B to point C? So we're using the same diagram, all that kind of stuff. What? So here's our A, B, and C. We know this distance is 25 meters. So if we start at point B and we end up at point C, our potential energy is what? Everyone agree with this equation? Okay, what do we get? Okay, does it make sense that this answer is a smaller number, okay, or a bigger negative than our last answer? Okay, because we're traveling a greater distance. That means we're picking up more speed. Okay. And that time we were relative to point B instead of point A. Okay. So we're going to look at a couple different types of potential energy besides gravitational. Okay. We're going to look at elastic things and things that are coils or springs. Okay. So take a look at this picture of a spring. This is the compressed state in the middle. This is the stretched state. This is just its static, regular, nothing being exerted on it kind of state, okay? So if these are compressed and, if these are compressed and stretched the same distance from the start, which has more potential energy? How many of you think the compressed one has more potential energy? Raise your hand. How many of you think the stretched one has more potential energy? Raise your hand. How many of you think they're going to be the same? Yeah, they're the same. Okay. If they are stretched or compressed the same amount of distance, okay, it's going to be the same potential energy to get back to its static position. Okay, or original. Okay? So those are the two types of potentials that we're going to look at. We have an equation specifically for potential energy of a spring. Okay? So you need to kind of make a note that this equation is used for springs only. Okay, so here is our equation kind of for a spring. When we exert a force, the only reason I put F person is because we need to know that that's an applied force of some kind. Okay, we could have put applied or whatever. You just need to know that this is a force that's applied, holding this spring in a compressed or a stretched position at some many x meters from its static location. Okay, so force exerted equals K times x. K is what we call a spring constant. The spring constant is individualized for each and every spring. Okay, it is dependent upon how thick it is, at what degree it is wound. It's just basically how difficult it is to compress or to stretch. Okay, but each individual spring has a spring constant. You'll be given that. You don't have to memorize any of those. Okay, that's not something you'll be expected to memorize. You just have to know what K is. Okay, so remember Newton's third law says equal and opposite reactions. If I exert a force on the spring, that spring will exert one back to me to restore itself to its static position. Okay, so this is force of the spring is negative K times x. Okay, this is called the restoring force. Okay, this is the spring exerting a force to restore itself to its static position. Whether it's been stretched or compressed, it doesn't make a difference. It's just a certain x or a certain distance in meters from its original static position. Okay, this is called Hooke's law. Okay, the spring equation, not so common. Hooke's law is very, very common. So if you go on to take college physics, you'll hear about Hooke's law a lot. Hooke's law has to do with springs. Okay, which is a little bit counterintuitive, but it is. Okay. That's Hooke's law right here. What? I accidentally clicked forward, and then I went backwards. Okay. Does everyone have what they need? All right. So this is our elastic potential energy equation for springs only. Okay, remember whenever we see this K, we know we have to be dealing with a spring because K is a spring constant. So this equation is only used for springs whenever you see that K in there. The last one we saw was for the force of a spring. This is for potential energy of a spring. Okay? K is the spring constant and x is the distance from the static position. So whenever we see that K in an equation, we have to know that we're dealing with springs or coils.